All right, so in this video, what we're gonna do is we're gonna learn to put the electrons in the atoms in the way they should go. Basically, we're gonna build make a blueprint for how the electrons fit inside an atom. And the reason this is important is later in the year, as we talk about all the reactions that can occur and all the ways that different atoms interact with light. For example, to give color, there's a reason that purple dye, or the purple or red in your shirt, is purple and red, and it has to do with exactly where the electrons are located. So before we get to that, though, let's just start with the basics, and that will be our basic electron arrangements. So from the last couple of videos, we know a couple things about electrons. We know that they existed in an electron cloud, and that electron cloud has energy levels. Much like floors in a building, there are energy levels. 1, 2, 3, 4, and so on. The energy levels, for later, this will come in handy, they're given the abbreviation N. So if you see N, that's talking about energy level. Then we talked about sublevels. So there's an S sublevel, a P, a D, an F. You might think, well, is there anything besides an F? There is. However, there is no atom that uses the G sublevel yet, because the biggest atom only has 117 electrons, and 117 electrons can fit into the sublevels that we have now. So in the future, sure, there might be need for the G sublevel. And I will tell you that sublevels are abbreviated with the letter L. Okay, so for now, we'll just deal with energy levels and sublevels. We also, in the last video, talked about the Pauli exclusion principle. The Pauli exclusion principle tells us that when two electrons are in an orbital, one needs to be spin up, the other needs to be spin down. They cannot both be spinning in the same direction. So, let's take a look at how we would do this for hydrogen. Alright, so there's two ways that we can write out how the electrons are arranged in an atom. The first is known as the electron configuration. So for hydrogen has one electron. So when we looked at the picture before, and we had the energy levels, so N, maybe it was like this. The first electrons have to go in the lowest energy levels. And this is known as the Aufbau rule. Aufbau says that the electrons go into the lowest energy level first, so the first electron will always go into the first energy level. That's the Aufbau rule. Basically, when somebody comes into the hotel, they go to the first floor. Makes sense. So that means for hydrogen with one electron, the electron, we're going to give it an N value of 1. And if you remember, the first energy level only has s orbitals. So that electron has to go into the s orbital, and there's one of them. So I put a 1 there to show that there's one. This is what is known as the electron configuration. Now, for those of you that are artistic, you can also do what's known as an orbital diagram. An orbital diagram looks like this. You draw the number of orbitals. In this case, there's only one orbital. It's an s orbital, and it has one electron. So you get to choose if it's a spin up or a spin down. So we'll do a spin up, and above that you write what energy level and what sublevel it's on. So this is known as the orbital diagram. Okay, so that's hydrogen. And so let's do the next element. We'll just put a red box around off ball so we can remember that. So let's go to helium. Whoop, let's do it in black. So let's go to helium. Helium has 2 electrons. Okay, so the electron configuration, our first electron goes in the first energy level, S sublevel. Again, we're going to start with the 1s because of the off-ball rule. And now we have 2 electrons. Can 2 electrons both fit into the s orbital? Yes. So 1s2. There's the electron configuration. The orbital diagram now, we have 2 electrons. So spin up, spin down, and it's still the 1s. And that's it for, we've just done now, hydrogen and helium. Now let's take a look at some more complicated elements. Let's take a look at, well actually let's first, I put the wrong picture in here. Let's take a look at lithium, which is right here. Okay, so it's got 3 electrons. So lithium has 3 electrons. So it's going to have electron configuration. Do this in blue. 1s2. We already saw that the first 2 electrons, because of helium, will go into the first energy level, S sublevel 2. Now, we have 1 extra electron in lithium. It has 3. Where will the 3rd electron go? Well, if you remember, we're going to move up to the next energy level. So if we have n equals 1, whoops. Nope, I'm going to do that. N equals 2. And on the n equals 2, there's both an S and P. So, but we first got to put it in S. S comes first. So this is going to be 2s and then 1. That will be for lithium. Let's do the next one. Beryllium has 4 electrons. So it will be 1s2, 2s2. The orbital diagrams for each of these. There's 1s. And you can write the 1s, or you can write the information below or above the box when you do an orbital diagram. Badass. And this is 2s. Here we have a 1s with 2 electrons. And then we have a 2s with 2 electrons. So that gets us through the first 4 atoms. What if we get to boron, which has 5 electrons? Boron has 5 electrons. Well, we probably can tell that the first 2 will go into the first energy level, the S sublevel. The next 2 electrons will go into the second energy level's S. And then now we have filled that S, but we still have 1 extra electron. So where will it go? Well, if you remember, the second energy level has 2 sublevels. One's the S, the other's the P. Well, now we can start to fill the P. So I put a 2, and I put a P there, and it's got 1. So there's the electron configuration. The orbital diagram will look like this. 1s will have 2. 2s will have 2. I'll get rid of that. And now, when we write the p orbital, so the p sublevel, sorry, since there are 3 orbitals, we've got to do 3 boxes. This is the 2p. And again, see here, we've got 1 electron in the 2p, so we can put it in any of those boxes, and let's do spin up. So let's do one more here. Let's do carbon. Has 6 electrons. So we know the first 2 are going to go in the 1s, so 1s2. Second 2 will go in 2s2. And the next 2 will go into 2p, so it'll be 2p2. And what you can see is each following atom looks exactly like the atom before it, except you add one electron. So these electron configurations basically copy each other, except you add one more electron for each element. So now, what will this look like? We've got our 1s with a spin up and a spin down. We've got our 2s, a spin up and a spin down. And now we have our 2p. So we put our first electron in the first one. Now, this is the last rule that you'll have to know here. And this is called Hund's rule. I call it the bus seat rule. Okay, and the reason why I call it the bus seat rule is we have one more electron to put in here. And we could put it right here in this orbital that already has one electron in it. But instead we're going to put it here in the empty orbital. And the reason is because it's less energy, it's easier, in other words, for the electron to go into an empty orbital than for it to go into this empty orbital or this empty orbital than to go into one that already has an electron. And it's similar when you get on a bus. If there's an empty seat, most people will sit in the empty seat before they sit with somebody else. And it's the same thing with electrons. So whenever you're filling a sublevel that has multiple orbitals, you fill each orbital with one electron before you pair up two electrons. So the next element's nitrogen, and it has 7 electrons. So nitrogen, we'll put this 7th electron there. And it's not until we get to oxygen, which has 8, where we'll put a second electron. And of course, Pauli exclusion principle, one of our other rules tells us it'll be spin down and it'll go there. Okay, so we'll practice in the next video some more difficult ones.